Okay, guys, so we're starting now. We have over 30 people on our webcast throughout the world, so that's good. This is our first meetup over here in this office, and we'll have a series of them over the next few months and going forward. And before we start our meetup, a shout out to Ampool, the sponsor of the pizza. And thanks to Ampool. Today we're going to have two talks. One from Capital One, Ilya, talking about next generation decision making under 2 milliseconds. And second by Brian from Hortonworks, how to integrate an i5 with Apex. So with that,
I think it works. Can you hear me? Right, I'm talking. Hi guys, so my name is Ilya. I am part of the Vault 8 team. I'm a data engineer in Capital One. And broadly speaking, our team is a data innovation lab. And so our role is to go out, find the latest and greatest technologies, and bring them in-house to solve business problems. So what we're going to talk about today is arguably one of the hardest problems that we face as a business, and that's how do we very quickly make decisions on the data that we consume. To that end, we went through an extensive evaluation and investigation process to essentially figure out what is the right solution for the problem that we have at hand. And this talk is the story of that process. Okay, let's try that again. All right. So broadly speaking, big data gets thrown around a lot. Fast data gets thrown around a lot. I'm going to take a second and actually define what I mean when I talk about these things. As far as big data goes, in my mind, what we're really talking about here is just the sort of stereotypical batch processing. We have a bunch of data that's landed somewhere in memory, on a cluster, on disk, what have you, and we can apply sort of our traditional methods to operating on this data. Now, scaling out to process more data is still hard, right? You still have to sort of go through the exercise of figuring out how do you add more machines, how do you have these machines communicate efficiently, and how do you deal with limitations of something like the JVM when you're worrying about scaling out. But the one thing that you don't have to really worry about is how long it takes you to actually process this data. Typically, when you're dealing with batch processing, you're not going to have sort of a critical guarantee that you must provide a response in a very small window. So you might need to get a response out in a matter of seconds or in a matter of minutes, but it's a lot easier to work on those timescales than when you're working on timescales of microseconds or single-digit milliseconds. We have to have a use case where we do need to work on that timescale, where we need to generate a response in under 15 milliseconds for any single transaction that we see in our system. And this means that we're in a second realm. We're in the realm of streaming. And in streaming, we're not operating on chunks of data at a time. We're really operating on one piece of data at a time as it comes in and becomes available to us. And this distinction matters because if you consider a batch of data that you process, the very first tuple that you consume is going to be waiting for the other 499 pieces of data that come in before that batch of 500 actually gets processed. And what that means is that the time it takes to generate a response for that very first piece of data is potentially very long. Because not only do you then need to operate on that batch, but you also need to wait for all the other pieces of data to arrive. In contrast, in stream processing, as a piece of data becomes available, it immediately gets fed through the pipes, operated on, and you get a result out. Now the challenge here is that we can't simply say, oh, well, we can just take a little longer to process this, right? We want to throw a few more algorithms at it. Because if we do that, we're going to increase the complexity of the system, and we might exceed the time window that we have. What this means is that, realistically speaking, the only way that we really deal with the challenge of processing a lot of data in the streaming fashion is that we have to scale out. And so the question of how efficiently and how easily can we scale out in a way that still maintains the reliability of the system, it makes it easy to deploy it in an enterprise environment, that actually proves to be the hardest challenge. The sort of traditional solution to how one does this is that one essentially throws money at IBM. You buy mainframe hardware. These are specialized computers, highly optimized. All your code runs on these arguably restricted machines, so you have a very limited, essentially, set of functionality available to you. But these machines are blisteringly fast, and they never break. Right? On the flip side, you've got the open source world. And open source offers a whole wealth of advantages in its own right. You can customize the code to do whatever it is that you want to do. You have the ability to grow the project organically. But you are almost never going to get the same degree of reliability or performance that you will get from a system that's built for production and that came from an environment where if things break, you're going to get sued for millions of dollars. So the biggest advantage that you really have from these mainframes as far as a business is concerned is this notion of availability. For everything that happens on these systems, you have a strict contractual guarantee called an SLA of what that system must deliver in terms of performance. Now, the key metric as far as we're concerned is this measure of downtime. Essentially, what fraction of time in a year will this system be out of commission and unable to produce a response when data arrives? And we care so much about this because any time that we do not generate a response to an incoming request, we're sacrificing all of the investment that we've made into creating the systems that respond to that request, because something upstream of us will just make that decision for us. In this realm of mainstream computing, your measure of how performant your system is, in terms of availability, is typically measured in nines. And what these systems guarantee us, typically, is at least 5 nines of availability, meaning that in a single year, you'll have just barely over 5 minutes of unplanned downtime. You've also got systems like S3, which actually guarantee 9 nines of availability for comparison, which means that for all intents and purposes, these are never down systems. To get this, you pay a lot. Now, with open source technology, there's a massive advantage, first and foremost for the business, because it's free, right? If you can get this thing to work, that's a huge payoff in its own right. Secondly, these systems are notably more flexible. You don't have to go to IBM or Oracle or somebody else and try to convince them to add some feature to the product that benefits your business specifically, but may or may not affect anybody else. They're not going to care unless you're a giant paying customer. With open source, if you have the know-how and the familiarity, you can go and build it yourself. And in a lot of ways, this allows you to future-proof whatever you design on top of these systems. And that's a critical sort of goal when the ultimate objective is to build systems that last well into the future, where our solution to problems is not simply to just throw more money at it. Now, what we do today is we have data come in. We're a credit card company. Somebody swipes their credit card. And we have something called a model. And a model is merely a box that makes a decision for us, given some set of input data. And I'll dive into in a moment what that means in a little more detail. These things get fed into a mainframe, and then we throw money at the problem and hope that it goes away. Now, the issue here is that at some point, it's questionable whether we're throwing an appropriate amount of money at the problem or whether we can come up with a better solution that is a little more future-proof than being utterly dependent on outside providers of hardware and of software that makes decisions for us. Now, a model is merely something that, given some input data, so in our case, say the spend amount for a transaction, and generates a response. In this case, say we want to predict the likelihood that you're a millionaire. And we might want to do this, for example, if we want to offer you a bigger credit line. Now, the features that actually power this model are sort of the signal that we create from the data. And in our case, we have 3 real classes of features. The first we call simple features. These are pieces of data that are present directly in the transaction as we receive it from the upstream provider. Right, this is going to be something like the date of the transaction, the location, the merchant, pretty much the basic stuff that you'd expect. You might be able to get some useful predictions out of that, but what has substantially more value is a second class of features, what we call velocity features. And these are aggregates over time. Now, you can think about this as the amount of money you spent at a particular store, or the sort of distribution of how you spend money over geographic regions, right? So if you're normally buying lots of things in Maryland and all of a sudden you're spending in Texas, then that's a wonky situation. Now, the consequence of needing to aggregate data over time is that all of a sudden in our stream processing solution, where data is coming in one piece of data at a time, we now need to maintain a notion of state. And we need to efficiently aggregate this data over time and be able to query it quickly because we still can't exceed this very tight latency window that we have. To that end, this data gets stored in an in-memory database. And now, the reason that this has to be in memory is, if you're familiar with sort of the latencies associated with the disk read, if you hit hard disk, you're already incurring a 100 millisecond penalty. So a lot of frameworks will not worry about this because they don't have these very small latency windows to worry about. So for Kafka, for example, to ensure durability, they're backed to HDFS, which means they can always replay from HDFS in the event of a failure. But if we have to replay from disk, we lose. We're already not able to make a decision within our live latency window. So everything we do essentially must happen in memory. A last class of features that we consider is something we call advanced features. And these are features that combine multiple sources of data and distributions of data over time. For example, this can be the amount that you spend in a particular geographical region as a function of time. Right? So these are more complex aggregates. And for this third class of features, depending on the timescale, it may actually be okay to aggregate these in batch form and load these into the in-memory data store to be queried readily. So in a sense, we have a system combining a lot of different kinds of data and different ways of operating on the streaming data so that we can ultimately make a decision quickly.
So what is the in-memory database you're using?
I'll get to that. I can address that now. The in-memory database that we're using at the moment is HDHT. It's a memory store built into the proprietary offering of DataTorrent, not baked into Apex. We've also built a solution on top of Redis, demonstrated similar scalability. What I would like to do at the end of the talk is dive into in a little more detail why we are using HDHT at the moment and what our goal is sort of for the long term to avoid being dependent on a proprietary piece of technology.
Hazelcast as some of the Wall Street guys do.
No Hazelcast. We did evaluate Ignite as another comparable compute grid for doing some of those. I'm sorry?
You did the Apache Ignite?
Yes, we looked at Ignite early on.
And how did it go?
Not so well.
Huh?
No. But again, we're getting a little sidetracked, so I'd like to keep things rolling. Where we are right now is that we have a system that is extremely stale because, again, updating the system costs lots of money, meaning that we don't update the system very frequently. When the system is stale and the models that it executes are stale and out of date, we can't really make good decisions. And so at some point, the refresh cycle rolls around and we ask ourselves, can we not do this whole thing better? Can we not get out of this terrible swamp, stop throwing money at the situation, and actually wind up in a place where we're happy with the system that we have? So this is all well and good. We are ultimately, however, building something for the business. So we have to do more than just find the latest, sexiest technology, make a prototype, say, hey guys, this is going to go do great. Just throw 1,000 nodes at it on AWS, everything will be dandy. It doesn't really work that way, especially when you're trying to sell things to a bank where their primary motive is to avoid risk at every point in turn. So everything that we do has to have a rigor associated with it. We must essentially prove that whatever solution we pick makes sense both from an engineering perspective, from an architectural perspective, and that it's feasible to deploy within the enterprise. This is the only bit of actual hard text on here. And I want to just highlight a few things here that at first glance might not seem like that crazy of a deal, but are actually critically important. We've already talked about our latency constraints. The second bit, so this goal of 2,000 events per second, right, is laughably small. I'm not going to sit here and tell you that that's a lot of data. But the thing to keep in mind is that this is the raw data that's coming in. And as this raw data comes in, on top of this raw data, we need to compute features. We need to retrieve features from memory, right? We need to compute and retrieve more advanced features. We need to update all of the pieces in memory that we're maintaining in terms of aggregates, right? And ultimately, we need to feed all of these into a model, make a decision, score it, validate it so that over time we can track when our model performance degrades and we know when we need to deploy new models, and then ultimately return a response. And now all of this still needs to happen within that latency window. And what you actually see is that these 2,000 events blow up, and these turn into hundreds of thousands and millions of events in their own right. So this number, which at first seems really small, in reality blossoms very quickly. Now, we've talked about the importance of availability. If we want to replace a mainframe, if we're building something on open source technology, then we have to meet these same requirements for availability and durability. We cannot lose any of the data going through the system, and we can't exceed our latency window. And the last bit, and I've spoken to this, is this notion of scalability. That as we need to process more data, as we want to grow sort of the problems that we're able to tackle with the system, then whatever it is that we select, we should be able to add resources without having system performance degrade. And that's really the only sort of measure of scalability that matters. Like, your ultimate goal is, right, you have a linear relationship, right? You can add 10 times as many nodes and you'll get 10 times as much performance. The sad reality of it is that you're going to get maybe 5 or X or 6X performance because of all the complexities of building a larger system. But the degree to which it's easier to operationalize such a system and keep it running, that's ultimately what drives its sort of long-term success. And the last bit, and I've harped on this enough, but sort of soft metrics. These are things that came not from the business, but from ourselves as a team, is that we really did want this thing first and foremost to be built on open source as much as possible. To future-proof it so that we're able to take our learnings and give them back to the community, and so that this framework is extensible, updatable, dynamic, and we never wind up in the situation in the future where we're stuck and our only solution is to throw a lot more money at the problem to make it go away, or to launch a massive engineering effort to fix it. So how do we actually get out of this swamp that we find ourselves in? And the only true answer here is that you must consider all the things. So Hazelcast is up there. We did look into Hazelcast. We didn't run it to the same extent that we ran some of these other frameworks. This is a small subset of all the things that we've looked at in terms of streaming frameworks, in-memory databases, compute grids. Of all of these, there's only a few really that stood out for our particular use case, and I'll dive into specifically which ones those are later. But the more important question is, how do we actually compare these? And first and foremost among this, anything we select has to meet our performance requirements. We have to meet our requirements in terms of availability, durability, latency. And the system must scale. Second to that is that this system must, in its present state, be ready for deployment in the enterprise. And now this is kind of a tricky thing to actually define, but realistically speaking, what it means is that we can take this, we can take our prototype, and we can go to the leaders of our business who do not want to take risks, because risk is expensive. And we have to tell them, this is not a risk. This is proven. We can guarantee that this will work. And of all of the things that we have to show, that's the hardest, right? That is the hardest thing to quantify. That's the hardest thing to convince somebody else of. To build on this, if we want to future-proof whatever it is that our solution is, we have to consider how it's going to evolve into the future. And that means looking at its roadmap. And this is both the published roadmap for this technology, as well as actually interacting with the folks behind it to understand where they're taking it and what they're building. Because a lot of the times, especially with open source projects backed by proprietary companies, private companies, this isn't necessarily public information. So to the extent able, we try to figure out, even if the technology is not there, where will it be a year from now, 2 years from now? And the reason we want to do this is that if we're putting all our eggs in this basket of a particular tool, we don't want this tool to go away from us and move in a direction that we can't really benefit from. And the last bit that sort of ties all of this together is the community around the project. Especially in the open source realm, a project lives and breathes by the people that support it and that help build it. And again, if your community moves away from you, you're going to be stuck maintaining a piece of code that nobody else is working with. New tools are going to come out that aren't going to interface with it, and you'll be stuck holding a piece of dead wood. And so anything that we selected, we wanted to make sure that it has a vibrant and active engagement amongst a broad and diverse population. Now, the upshot of this entire discussion is that of all the things we looked at, Apex was the only thing to fit the bill. And I'm not going to just sit up here, tell you that, and then walk away. I'm hopefully going to actually convince you of that fact. And to do that, we're going to look through the main sort of runners-up. We're going to consider Storm. We're going to consider Spark Streaming as kind of the elephant in the room. And we're going to look at Flink as the final and best alternative to date that we've seen to Apex. So first and foremost, I'm throwing Spark up here not because it's necessarily a viable solution, but because it's what everyone knows and I think to some degree understands better than any of the other tools up here. And Spark Streaming in particular is not really a true streaming solution. So under the hood, Spark Streaming is doing what is called micro-batching, meaning that it's taking the input data, it's waiting for enough of that input data to come in to reach a predefined interval of time or size, and then it is running that mini batch, which may be a couple seconds or a few hundreds of milliseconds, on the underlying Spark framework that does what Spark normally does, moves some data around, gets it all into the right memory space, does some computation, writes it out to disk. Now, the consequence of this is that all of Spark's internal machinery is still in the loop. And even if you can reduce the duration of this microbatch, as you can in newer versions of Spark, that machinery starts getting in the way, especially when you get down into levels of hundreds of microseconds. And pretty much in practical terms, you cannot really use Spark Streaming for applications less than half a second of duration in terms of latency. Now, the consequence of this is that if we wanted to build our tool on top of Spark, we could simply not meet our latency requirements. With that said, Spark is still a fantastic tool as far as quick and dirty ETL, rapid iteration with machine learning algorithms, and simply moving data back and forth in and out of various systems. And to that end, that is what we use it for. So in our ultimate solution, Spark powers one of these advanced features that we're talking about. We compute this feature in Spark, load it into memory, and subsequently consume it with Apex. Now, of the three true streaming solutions, each is different in their own right. And Storm up here is kind of the legacy solution, but it's also the most proven, right? It's been around for ages, deployed in production all over the place, blisteringly fast. It works. It's easy to use. I will dive into why it's not quite right for us. That said, it's still a great piece of technology. Flink is a much younger project, younger than either Storm or Apex, but very well designed, a bunch of smart people behind it, active and growing community, and they are doing a really great job of essentially explaining why they are a true competitor to Spark and why they're a great streaming solution. And part of this is that they have a really robust system for error handling that does not cause some of the same problems that Storm runs into. And last of all in here, we have Apex, and I'm not going to talk about it right now because I'm going to dive into in detail what makes Apex special after we talk about the others. So Storm is a technology that was acquired early on by Twitter and primarily driven by Twitter for a long time. What's interesting is that Twitter ultimately moved away from Storm in favor of Heron. That's something that happened earlier, or towards the tail end of last year, I guess. And the reason that they did this is because they ran into issues executing Storm in production environments, especially at scale. And part of the reason there is that essentially different Storm applications would not play well in the same cluster. And they ran into issues with resource sharing, amongst other things. The way that Storm works is you create topologies or connected graphs of operators. And in Storm, you have two kinds of operators. You have essentially a source operator called a spout, and you have bolts, which are operators that consume the source data, do some operations on it, and pass it on to other bolts in the topology. Now, the reason I mention this is because in order to understand how Storm handles failure scenarios, you kind of need to have a better, some semblance of the structure. Now, in a failure scenario, say for example you lose a node, you're going to lose the operators, the bolts or spouts that are deployed on that node. The way the Storm handles these failures is that when a spout initially produces data and emits it into the topology, it'll also transmit, it'll wait for an acknowledgement signal to come back from everything downstream that needs to consume that piece of data. Now, the way the Storm detects a failure is when this acknowledgement never comes back. And one of the first problems that you run into with Storm is that you can't actually configure this acknowledgement window to be less than 1 second. So what this means is that you can't detect a failure any sooner than 1 second. Now, in of itself, this isn't a disaster, right? What you can do is you can create 3 separate pipelines, all processing the same piece of data, such that if any one of those pipelines fails, then the other 2 pipelines will still be doing the same work, and you can get a response from one of those. This would work great in theory, except that unfortunately in Storm, because everything ultimately comes back to that same spout, and that spout needs to go back and replay, you have to reset the state of the entire topology. Meaning that the only way to actually create this independent, durable structure where you have these separate pipelines processing the same data to be independent of each other, you actually need to deploy separate Storm applications, which unfortunately brings us to the situation that Twitter found themselves in, where they're deploying a multitude of large Storm applications on extremely large clusters, but these applications were all competing for resources and competing with each other just for compute, and not able to operate efficiently. And the consequence of this was that they ended up redesigning Storm fundamentally to avoid a lot of these issues, and they built their own resource manager to replace the sort of default manager that Storm has to get around this. Now, what this means is that for the sake of scalability and fault tolerance, it's a lot harder to actually operationalize Storm. So that was kind of the initial strike against Storm. Now, a second bit that matters is we've talked about this notion of dynamism in the topologies. We want these topologies to be reconfigurable, and we want them to be dynamically scalable. And there's 2 reasons for this. We want these topologies to be reconfigurable because we want to be able to deploy living and breathing models that we can update either the model or the features that power them. We need to be able to reconfigure the graphs that actually represent the execution of our system. Secondly, as we want to process more data, as we want to add features to the system, necessarily we have to do more computation. And again, we talked about us being in a streaming environment, meaning that we can't just take longer to process. This means that we have to scale out. And having the ability to scale out dynamically means that as we encounter periods of heavy load, or if we have certain transactions that require a wider feature set, we can dynamically adjust our system to compensate for these changes. Storm does not, in its present form, support any of the sort of dynamism. You cannot dynamically scale it, and you cannot dynamically reconfigure these topologies. These are both things that are on the long-term roadmap for Hortonworks for supporting Storm, but these aren't things that are available today. The last bit is that as far as the community for Storm goes, Storm had a very vibrant and active community for a long time. Today, folks have moved away from it. There's not a wide sort of industrial backing for Storm. Hortonworks is, realistically speaking, the only true powerhouse behind it. Yahoo has 1 or 2 committers that are active for Storm, but there's not sort of a broad user base continuing to support Storm, and folks are definitely moving in the direction of newer technologies. The consequence of this is that it's difficult to sell the notion of a technology that's been around for a while, but is in a lot of ways kind of growing stale, and whose community is becoming equally stale and unmotivated to continue improving the product when it comes time to actually argue for deploying this thing in the business. So I am 1 slide behind. I apologize for that. We should be at this slide. Now, moving on. Next in our lineup, we have Flink. Flink is a technology that came relatively recently out of a group, I think, in Germany. It's actively used and sort of experimented with in research institutions all over Europe, so there's a pretty broad presence there. And at its core, it's based around the same idea as Apex and as Storm. You create connected DAGs of operators, data flows through these operators, gets routed appropriately. Now, what sets Flink apart from Storm from the get-go is that they have a much different mechanism for handling failure. In Flink, what they do is they inject what they call, I believe, buffers into the data as it flows through the system. And these buffers are replicated to every operator throughout the system. And in the event of a failure, you essentially track back to the previous buffer and only have to replay from there. Now, as these buffers flow through the system, Flink takes checkpoints. These checkpoints are stored to disk, and Flink is able to quickly and rapidly reload these checkpoints from disk in the event of a failure. Now, the consequence of this is that there's no notion of waiting for an acknowledgement from a piece of data flowing through the entire topology before hitting a failure and waiting for that response. So its failure handling is much faster than Storm's. And they do demonstrate that when they turn on failure handling in Flink, the equivalent to Storm's acknowledgement framework, they do not take a performance hit whatsoever in terms of latency end-to-end through the system. Now, the thing is, however, that this failure mechanism still requires a upstream data provider to persist the data that Flink will replay. And what this means is that it has to go back to something like a Kafka upstream that will be a source of ground truth for the data that it needs to replay. Now, the other bit is that, like in Storm, in these failure scenarios, Flink has to reset the entire topology to the appropriate state to ensure consistency. The consequence of this is, again, that we don't have an easy way to create durable, independent pipelines in the same system. Now, in terms of roadmap, Flink is presently working on adding dynamic scalability in terms of both sort of the physical partitions associated with each operator that allow it to process more data simultaneously, and on adding reconfigurable modules for its DAGs. Again, this is on the roadmap, not presently available. As far as what Flink does well in its present state, they have a much better API that's much easier to use, truth be told, than Apex is, right? This is an intuitive declarative API, similar to Spark's, and quite frankly, they've been positioning themselves as competitors to Spark, both in the streaming realm and in the batch space, and with good reason, right? They're a fundamentally sounder and more scalable architecture than that proposed by Spark. However, when it comes to sort of guaranteeing performance in failure scenarios and being enterprise ready, we did not feel comfortable as a team in actually presenting that to the business. Unlike Storm, which has provenly been deployed in a large number of production environments, Flink to date has only one customer that actually runs Flink in production. There are others. There are a number of other companies that use Flink in pre-production, meaning that they use it for ETL tasks, but they're not using it for critical workloads. And when we're coming to the leaders of our business and we're saying, hey guys, we want to run all of our transactions through this system, we can't offer them a system that hasn't been provably deployed in a business environment to date. Flink's community is young. It has generated a substantial amount of popularity recently. It's growing rapidly. They actually do a fantastic job of marketing themselves, and they do a really good job of communicating both what the framework is capable of and of describing exactly how it works, what it's good for. So to that end, I think they do a really good job, which is, quite frankly, why Flink is a very serious contender in sort of the space of solutions that we looked at. But again, because our goal is ultimately to identify something that we can take to the business and have it be ready for deployment today, right, given our proven prototype, we simply couldn't back Flink in the state that it is today. And this brings us to our last contender, and that is Apex. Apex is a technology that came out of Yahoo Finance. At Yahoo Finance, this was built by the team behind Yarn and Hadoop, where we have a number of them in this room. We've got Amol and we've got Fu. They can tell you a lot more about this later if you're interested. But in short, they were ingesting data from all over the globe, compiling it, doing data analytics on this data. And the system was built from the ground up to be reliable and to never fail. It was not built necessarily for performance. That was kind of a secondary objective. The first and foremost goal was that data should not be lost and the system should not break. And this puts Apex, which came out of this sort of closed environment, in a unique position. In that of the technologies we've looked at, it's really the only one that was built first and foremost for the business world and was then open sourced. And we can sit here, I think, and debate all day long whether it's better to have a technology that grows organically from the community or something that came from the business world and was open sourced as a ready-made solution. But the one thing that is certain is that it's a lot easier to bring something to a business and say, hey, here's a workable solution when it came from the business world. In Apex, as I mentioned, you create the same kind of workflow that you do in both Storm and Flink. You create a DAG of operations. Data flows through these operators. You can support, multi-input, multi-output design patterns. Data will get replicated appropriately. The part that I really want to mention here is this piece at the bottom. And you don't need to understand this explicitly, but what's happening here is that we're actually dynamically modifying this topology to add an additional operator. Now, Apex is the only technology that we've looked at to date that supports this level of interface in its present state with a live system. And this happens without sacrificing the stateful processing that's happening within that system. The second bit is that Apex does support this dynamic scaling that I've talked about, and we'll dive into that a little bit later. What an actual Apex cluster looks like is you have a Yarn system. Apex integrates arguably more natively with Yarn than anything else out there, again, being built specifically by the same folks that designed these systems to run on these systems. At the top level, we have this RTS app master. This is sort of a coordinating entity that tracks the heartbeats of the system and is responsible for sending a signal to restart any failed operations. This is itself a replicated process. It's not just a single entity, so there is a failover there should there be a need for it. And then on every node in your cluster, you may have one or more containers. Each one of these containers may have one or more operators. And the really interesting thing here is that in Apex, unlike in any of the other solutions that we've looked at, you also have the ability to actually specify the locality of execution. Now, what this means is that you can configure operators to be on the same node. You can configure operators to be in the same container. You can configure operators to be in the same thread. And the importance of this is that if operators are on different nodes, anytime you want to pass data between them, you're going to have a network hop, as well as the price of a context switch between the memory spaces. They're in different containers. You're not paying that network hop, but you are going to pay the price to switch context. And if they're in the same thread, the only price that you're paying is the same price that you would pay to make a function call within that application in that memory space. And what this means is that if you flip this on its head and you say, hey, now I can define affinity, but I also want to be able to define anti-affinity. I want to be able to say, okay, I want to guarantee that these operators run in different nodes. Then not only can we specify a performance metric that gives us better latency by running everything within the same thread, but we can simultaneously configure the system to be durable. Coupled with the last bit that I haven't mentioned yet, and that is how Apex handles failures. What we can actually do is these durable independent pipelines that I've been talking about, processing the same data, we can actually build them within the same application in Apex, and we can deploy these, and as a matter of configuration, make the system scalable and reliable. The way that Apex doesn't suffer the same sort of limitations as far as failure handling goes as the other systems we've looked at, where they have to reset the entire topology to source, is that for every pair of operators in Apex that reside in different containers, they actually have a buffer between them. The technical name is a buffer server. And this buffer server sits at the output of the first operator, and it acts essentially as a Kafka for any upstream operators that connect to that operator. So in the event of a failure, you never have to go any further back than to that buffer server, which is persisting this data in memory as well as durably backing it to disk. The consequence of this is that we never have the situation where we have to reset the entire topology in the case of a failure. And we can create these 3 durable independent pipelines within the same application, which dramatically simplifies deployment and operational maintenance. And we don't have to worry about resource conflicts of different applications running in the same environment. The last bit is that Apex does support this dynamic scaling that I've been talking about in terms of physically scaling out the number of partitions available to process the data flowing through the system. So each one of these separations represents the same logical processes being applied to different pieces of physical data. And Apex supports dynamically adjusting these based on statistics computed in flight at runtime. So you can scale based on throughput, you can scale based on latency through your operator, you can scale based on whatever else you want to scale on. But the point of this is that as your system runs, it will automatically adjust to different loads and to different challenges without sacrificing, without requiring direct involvement by a sysadmin or recompiling the program and redeploying it to your cluster. The last bit, and this is something that's in here because we use it, not because it's necessarily critically important for the sake of actually understanding why the system is valuable. But as data flows through the system in Apex, you have this notion of windows on top of this data. These are not injected into the data in the way that they are with Flink, but they serve a very similar sort of idea, which is essentially that you can take a windowed view of this data as it flows through the system, and then you can actually perform computations like microbatch and batch computations the way that you would in Spark or in Flink on the system. The advantage of doing this is that a lot of machine learning algorithms and a lot of analytics, things like join, group bys, what have you, actually require you to have a set of data to operate on rather than just a single piece of data. So having this mechanism in place makes the system generally flexible. We use this specifically for tracking latency through the system. We've actually engineered the system end-to-end to measure latency within every component, and we use this windowing metric to aggregate this data and visualize it in our program. So the actual performance that we get out of the system on a 600 gigabytes of RAM cluster, this is about, I think this was a 10-node cluster at the time, is that we're able to process 70,000 records per second with an average latency of 1/4 millisecond, well within our latency window. Now, the more relevant question here is what happens in the worst case? And that's why we have these percentile measurements here. And in the 6 nines case, in the 99.9999% case, our worst case measurement was still 6 milliseconds. So we are doing quite well as far as simply measuring latency there. Now, the bigger question is, okay, I've talked a lot about this notion of having durable independent pipelines. Let's actually prove that this works. Let's prove that we can feed in a bunch of data through the system, look at how many individual pieces of data take longer than our latency window to generate a response. Because you can imagine we have 3 independent pipelines. Whichever one responds first, we can essentially take that answer, say, great, we have a response, we'll send that upstream. And what we found is, after feeding 5 million pieces of data through, that we only had 39 of those records that exceeded our latency window of 16 milliseconds. And that fraction actually works out to be a success rate of 5 nines, as we needed to show. So we've demonstrated that we have a technology that meets our latency requirements. We've shown that we have a technology that meets our availability requirements. And the last bit, and this is something that's presently in the works, is that we need to show that any piece of data that enters the system leaves the system. And to that end, we generate a unique hash for every record that comes in, and we then compare against the hashes generated at the output to ensure that all the data that came in is equivalent to the data that came out. So
whoever produces the first answer, you run with that, and then you're done with it.
That's the notion. And the reason that this isn't formally defined is that this isn't actually something we've yet gotten back from the rest of the business. So essentially, the upstream consumer of the response that we generate, their operational paradigm is unclear. Like, we ultimately feed back to IBM MQ. What IBM MQ does with multiple pieces of data is undefined. So like, it's not like it's clearly articulated that it'll take the first response and append that. This is something that the rest of the business has not yet provided to us as a requirement. So to that end, we're working still in sort of this at least once paradigm. Now, Apex does support an exactly once approach. This is based, correct me if I'm wrong, on the windowing mechanism. But essentially, over the course of a window, you can ensure that you get exactly one response for every piece of data that comes in. So it is doable in the system. Our approach was always either A, the IBM MQ upstream will be fine with having multiple equivalent responses to a single incoming transaction, or B, we add a layer at the front that has a very strict heartbeat on it that will take the first response it gets and pass that upstream, or return without a success. So we consider this, we haven't had to implement it yet because we haven't gotten a strict sort of definition of what we actually need to build from the business.
So you assume that all of your processes are deterministic, so the two pipelines produce identical results.
Yes.
This is not always the case.
Not always the case. We, however, do not, first of all, we're not dealing with stochastic systems in terms of the features that we generate. So if we're getting different results from the operations that we're doing, there's a bigger problem. The other bit is that having two pipelines, if you have two different answers, you can't figure out which is the right answer. If you have three pipelines, then you can make a better estimate, right? So now we're getting into coding theory, but there's options there as far as.
Particularly if during the pipeline you're looking at some other database task. So the state of that can change out of your control. So the two pipelines are going to hit it at different times.
Great question. So to reiterate, the question is, we have an in-memory data store. If we have these same pipelines hitting that database simultaneously, are they going to be out of whack? And it's a really good question. The answer here is that we don't actually deal with that circumstance. The reason for that is that within Apex, we're able to explicitly control how we partition the data in flight. So we explicitly define the partitioning scheme such that the same operators will always see the same pieces of data for example, for every account, right? And so what this means, in addition to this data being partitioned, now is a good time to actually dive into what we're using as a memory store. And this HDHT that's built on top of data torrent, the way that it works is that it's essentially a way for the memory space of every operator to be stateful, meaning that in the event of a failure, it's durably restored, and for it to be persisted to disk over time. The consequence of this is that there is no sort of multiple pipelines hitting the same database. Each pipeline and each operator has its own memory space that it's using to store data. And so we never have this conflict where we're competing for access to the same database and we have to worry about concurrency issues.
So the two pipelines that they have, each one of them has its own partition of the data.
That's right.
Separately?
That's right. And by virtue of that, this never becomes an issue. In the case where we initially built this on Redis, right, totally would be an issue. And this is one of the reasons we moved away from Redis, along with other issues that we ran into as far as scalability goes. Now, long term, I did mention we don't want to be dependent on a proprietary solution. We are in the process of defining what does a next-gen in-memory database look like that'll serve the needs of this project, and are actually defining what that would look like and how we would build it, and ultimately open source it. So that is actually a presentation, so we are at the question section, so that's great. Yes?
So did you try Redis cluster at all, rather than Redis itself?
I'm sorry?
Did you try Redis cluster at all, or did you try Redis cluster rather than just Redis?
So we were running a Redis cluster. We scaled from a single Redis node to 3 Redis nodes to 10 Redis nodes. Performance-wise, Redis actually does great. Like we ran the same benchmarks. We only saw maybe a 1 to 2 millisecond degradation in terms of latency to Redis. The downside with Redis is that we would see GC pauses, which meant that our long tail would kind of grow out, right? So our percentile, our high-end percentile measurements were not as good. So we'd have more records that exceeded the latency window. And the other sort of challenge with Redis is that it has this client-server model, where at the end of the day, everything is going through a single server that's being replicated to the clients, and what happens when that server goes down How do you dynamically reconfigure things without downtime? So that's why HDHT is sort of a better solution in our case. Yes.
Any questions on the webcast? We have about 30 people there. Pramod, any questions?
Quiet crowd. I'll take it.
No.
Actually, I have a question.
Sure.
What's the HDHT API that you are basically are you just using it to store the state of checkpoint the state of operators, or are you actually using it to as a destination for your data?
Mm-hmm. We're using HDHT as a key value store to store features associated with an account. So anything that we need to maintain an aggregate for, we define a key function for it that goes into HDHT for each operator. So the memory space associated with a set of accounts will store the features associated with those accounts, and then we can quickly do lookups on those and update those as new data becomes available.
So the same account may be stored multiple times because it's used by different operators?
Yes. When we're replicating data, each of these 3 pipelines will see.
So you're not updating the account as you go through the stream?
In what sense?
Updating the account record or not?
Yes, we are.
Then there are multiple copies, then how do you keep them in sync?
There is no, I guess, your question is, what if the 3 pipelines get out of sync with each other?
No, so you've got 3 operators,
Yes.
all of them they're doing something with their account record.
Hmm?
So you say you got 3 copies of that account record per operator, right?
Not per operator. So again,
Oh.
there's a physical separation. So logically speaking, we have 3 independent pipelines.
Yeah.
Each of those 3 pipelines sees a copy of a single record for any one transaction, and we take the first response for that specific transaction that we get out. So the state of each of those pipelines will be in lockstep because they're processing the same data at the same time in order.
Yeah, I got it. So
Okay.
it's, okay.
Yeah. Hope that helps.
Did you consider SAMSA?
We did look at SAMSA. The main sort of strike against SAMSA is simply that it's built on top of Kafka. Kafka is back to disk, and that complicates the sort of situation of recovering from failures. Granted, this notion of parallel pipelines totally is fine in that case. Like SAMSA is arguably a pretty appealing technology. We didn't evaluate it explicitly. Again, relatively young, relatively small community, relatively focused support, right? Only really deployed at LinkedIn. So it was on our radar. We never did an explicit evaluation of it. We had 3 good alternatives. We have limited resources. We can't look at all the things. So we knew of it, think it's good, didn't use it.
Any questions from folks on the webcast? No. Okay, cool.
How's that?
Thank you. So our next presenter is Brian from Hotworks, and he'll talk about NiFi integration with Apex and NiFi itself. So before he starts, let me just saying this is our first meetup over here in this office, and so far so good. And it's a team effort. All of us work to get this going. But I'd like to call out one person who really made it happen, Shaber. All the chairs and everything. It requires a lot of logistical work that she put together. Thank you. Cheers.
Good.
Right?
better.
Can everybody hear me? Hello? Good. Sounds good? Okay, cool. Well, I appreciate everybody hanging in there for another talk. So I work for Hortonworks on the Hortonworks data flow team, and I've worked on a couple of these integrations between NiFi and other systems. So tonight I'm going to talk about some of the work I did between NiFi and Apex. Just show of hands, has anybody here already used NiFi or have any background with it? I'm kind of assuming not many people. Okay, one. All right, so kind of the way I was going to do is give some introduction to NiFi, just so that the rest of the talk makes more sense. I wanted to dive into this capability in NiFi that we call site-to-site, and that'll make a lot more sense when we get into the streaming integration and why that is. And then we'll talk about the operators that are in, will be in the next release of the Malhar operators. And then dive into a specific use case of kind of an example of how you could tie these technologies together in an architecture discussion. Just my background, I'm a NiFi committer and PMC member. I had joined a company called Anyara that was a company started to support NiFi by the original creators of NiFi. And that company then got acquired by Hortonworks, and we became the Hortonworks data flow team. And that's where we're at right now. And I tend to always work on these integrations between NiFi and other, analytic platforms, different storage systems, HBase, Solar, syslog, things like that. So just kind of jumping into NiFi and what it is. I think when people first see it, they try to compare it to some of the other tools that are out there and try to figure out like what is NiFi. So it's all about moving data around and bringing data from sources to the platforms that do the processing and back and forth, right? And if you think about how this happens in a large organization without NiFi, it's probably a lot of different tools pieced together, right? There's probably custom scripts, a couple of different technologies, cron jobs, all sorts of things, moving data around this organization. And you might get something working, but you kind of don't really know how the whole system fits together. If things go down, you don't always know. It's hard to react to changes if you need to change it, right? So NiFi kind of grew out of the need to solve all those problems. Like, how can we understand this data flow across the whole organization? And instead of having somebody draw this diagram that gets out of date of how everything works together, we want to actually see the data flow. We want to change it. We want to be able to react. If somebody says tomorrow that this data source has to go over to this other system, we don't want to have to write new code, stop the whole system, do a deployment. We want to just make that change right now when the person says to do it and have that change take effect. So it's not a analytic platform or anything like that. The job is to bring the data to the analytic platforms. And so we'll walk through some of the core features of NiFi. Some of the terminology just to kind of get everyone on the same page. So a flow file is a message that moves through NiFi. And the name flow file doesn't really have any meaning. So don't think that file means you can only move files. Just think a message. It has a payload and it has attributes. And it's kind of like, you could think of like an HTTP message. It has headers and the content, right? The reason this is important is because the attributes are passed around in memory. So they let you do really quick, lightweight operations. And the content is only accessed when it's needed to. So if you're moving like a 1 gig flow file through the system, you're not always moving 1 gig around, right? You're only doing that if the processor needs to do something to that gig of data. But you might be moving it through all these processors, making decisions, only accessing the attributes. The processor is kind of the main component that performs work on these flow files. So it could be a processor that pulls data from somewhere, a processor that delivers data, or a processor that does some kind of logic in the middle, like transformation, filtering. But the idea is that it kind of acts on one flow file at a time, right? And between two processors, there's a connection, which you could think of as a queue. And these queues, we'll talk about this more later, but one of the cool features is you can have these different prioritizers on your queues. So you can make very fine-grained decisions at every point in the data flow as to like how to bring back certain data sets based on their level of importance or maybe their age or things like that. And then process groups is just a way to sort of organize, your data flow. So I think like a common question we get asked is how to make multiple data flows in a single NiFi instance. We kind of view it as this one big data flow, and you can have these disparate groups that are not really connected to each other. Each group can then have like its own flow underneath that. You'll see some more about this later on. So this doesn't really do it justice, but it's just like a real small clip of the NiFi user interface where there's two processors drawn on the screen. So you get this canvas, you start dragging the processors on, connecting them, you start and stop them, and everything you're doing to them, like when you stop that processor, that's happening immediately, and the data is queuing up between them. And then when you start it again, that data is flowing through again. So there's also a lot of statistics and information you can get about what's going on in the data flow. So you can imagine a much more complicated flow here, and you have a pretty good idea of how things are connected, where there's problems. If any problem happens, like if one of these processors throws an exception, there'll be bulletins on that processor with the error message bubbled up. So you can immediately kind of glance at it and say, how does everything look? Is it working, right? And get a lot of information about it. And you can also take any part of your flow and create a template and share it with someone else. This is a really nice feature for debugging. If somebody creates the scenario and they say they have a problem, well, you just ask them, can you export your flow to a template? Give it to me, I import it, and of course there's like some settings you might have to tweak that are to each system, but you can see exactly what they were trying to do in the flow. So provenance is one of the kind of main features in NiFi. The idea of provenance is that we want to be able to track for every message, everything that's happened to it as it's passed through the system. So you can think about compliance scenarios where somebody comes back to you and says, we need to know if we delivered this data to the system because it shouldn't have went there or something like that. And we want to go back and see, what data did we actually deliver to that system? Or there's one specific piece of data that shouldn't have gone down this path, and we want to know did it. So we can go into provenance and we can get this, we get this list of events, and for any event, there's also other advanced search capabilities, but if you drill in on any event, you can get this graph of the events that happen. This is a very simple example where we had a receive event, which usually means that a processor, data was being pushed to a processor. So you could think of like a processor that has maybe an embedded server. It's like listen for HTTP event coming in. It registers a receive event, and then a send event. I think in this case it was sending it to Solar. And then the drop event just means like that's the end of that piece of data in the flow. But imagine a much more complicated flow where one message gets divided into several or more messages. You'd see that fan out in the graph, and you could track it all the way down to the end, right? So this is a really powerful, even just when you're like starting out and building new data flows and you want to figure out what's going on in the flow. I use this all the time to just come in here and say, between two processors, what did the message look like? You can drill in on the content at each point in time and see what it looked like. So if one processor says, I'm going to convert this from CSV to JSON, and you want to know if that's working correctly, you can just go in here, look at the processor before that, see the CSV file, look at it after, and see the JSON, right? Getting into the prioritization that I mentioned earlier. So, at all these queues between the processors, you can configure the queue and set certain settings. So you can adjust the prioritizer. You can actually build your own prioritizer. It's not a very common extension point, but you can. But the ones out of the box are the time-based ones, and then this priority attribute one. But what this kind of lets you do is if you had, say, 4 or 5 different data sources coming in, and they had varying levels of importance, you could tag each of them with a level of priority, funnel them down together, and then configure this queue to order them based on that priority attribute. So that everything coming from source 1, if that's priority 1, will get pulled first from that queue. And you can do this sort of throughout your whole flow and create this very fine-grained decision.
So the data provenance, I'm really intrigued about that. Where is this data provenance actually stored so that people can look at it? Is it like a SQL-backed database, or?
I'll jump into it in an architecture diagram in a minute, okay. But just the quick answer is it's not dependent on any other technology like other data store. It's internal repositories in NiFi, but I'll definitely tackle that.
Thank you.
In terms of extensibility, the whole, NiFi as a whole is built to be very extensible. So, everything, even the way that NiFi itself, the distribution loads everything that comes with it, is based on this concept. So there's 4 main extension points: processors, controller services, reporting tasks, and prioritizers. For any one of those things, you can build this NiFi archive, we call it a NAR, and deploy that into the lib directory, restart it, and then those are available there. It's using the Java service loader pattern, if you're familiar with that. And it's pretty straightforward if you're a Java developer and know Maven. There's a Maven archetype to get you going, and you can get something working pretty quickly. In the latest release, it's even easier. There's some scripting capabilities where you could just plug in like a few lines of Groovy, Python, JRuby, all that stuff right into a processor, and you don't even have to go through the Java model. But that's something to look into. There's some pretty cool stuff you could do there. Jumping into similar questions. So, what does the NiFi architecture look like? So a single node on the left is kind of your default behavior, right? If you just download the tar and start up NiFi, you get this single instance. It has a web server, embedded web server, which is Jetty, and it has these 3 internal repositories. So the flow file repository, think of that as the state of like every message and where it is in the flow. And it's like a pointer into the content repository, which is where the payloads of all those messages are. So as one of those flow files moves from processor 1 to processor 2, the flow file repository is being updated to say like where is it, what processor is it at. But it never necessarily had to read from that content repository unless the processor needed to read in that data. And the provenance repository is where all those events are. So these are all like custom internal repositories that are stored on disk. Generally, like a high performance scenario, you can, in the configuration file, you can specify a disk to put these on. You can have 3 separate disks for these. In a clustered mode, when you scale out, you have this cluster manager, and then your slave nodes or your data nodes, right? And the cluster manager doesn't do any data processing, but it's like the central coordinator. It's basically where you access the user interface, and all the changes you make are then pushed out to the other nodes, right? But it doesn't do any data processing. And I think a big difference from the cluster in NiFi to some other platforms. So we're not taking the graph of processors and like dividing them up and running certain processors on one node, certain ones on another node. Each node is running the exact same flow. It's just the data that is being divided across the nodes. So it's kind of up to how you're architecting the system and where the data is coming from to determine like how that data is going to be divided up, right? If it's somebody pushing you data and it's like a protocol that can be load balanced, you could stick a load balancer in front and you'd have a processor on every node getting round robin data. If it was pulling data, there's different approaches you can do. But just keep in mind, so it's the same flow on every node. That's kind of the takeaway there.
So what is the granularity of your profile? Is it like 5 megabytes for 100,000 IoT message bash, or it is like 50 bytes for each IoT message?
It could be either. So it could be.
It is a lot of tracking if you go to that level of granularity. Like
yes.
bytes.
So definitely, if you're doing very small, frequent messages, then there's going to be a threshold, right, of how long you can keep that provenance data around and things like that. So for each of those repositories, there's different like age-off mechanisms that you can control. So it's like we're not viewing it as where the permanent storage forever of every piece of provenance. Right. So the idea is, so the questions are around the provenance data and for like high volume small messages, about storing all that. So we would definitely have a time period where we could store that. And then if your situation was where you needed to keep that data more permanently for some longer period of time, there's ways of pushing those events out of the system to, you could build some other kind of custom data store, maybe like an HBase store or something like that. But yeah, so we view it as a certain time range, right, of that data that we can keep around.
So the flow file repository is replicated, whereas the content and provenance repository is completely local. Is that
they're each actually local, right? So if you think about a flow file, it can never actually move across nodes in the cluster because they're each running the same flow, right? So on one node, that flow file had to come from some source that either got pulled in or pushed in, and now it's on that node. It passes through the graph on that node, and then it's either, something's done to it, right? It's delivered to somewhere else. And it's never going to cross over to like node 2 in the cluster. So each one has its own repository.
Is there a versioning involved in any of these repositories?
I'm sorry, say that.
For flow file in particular, is there a versioning involved that
Version.
I push a new flow file and basically the older one remains there?
Yeah, you can. There's definitely a couple of different ways you can do it. So you can. Sometimes you might have a flow file and then you want to transform the content. So you're like overwriting the content with new content. Other times you might be spawning one or more child flow files off that one. So usually in that case, you'd create like n new flow files and you'd remove the old one. And usually coming out of a processor, a lot of processors allow you to route the original one somewhere, but also route like new ones that something might have happened to, things like that. Okay, so that's kind of the quick NiFi like 101.
So I have a question. People on the webcast.
So you mentioned here that the container repository and the flow file repository they are all local. So what will happen if one JVM or one host is down? How to recover from the failure?
Yeah, so there are a couple of things in the works to handle some scenarios like that. So right now, I guess the two scenarios that could happen is the cluster manager could go down. In that case, the data nodes still continue on processing fine. It's just you need to bring the cluster manager back up to access the interface. If one of the data nodes goes down, that node is down right now, like it's not replicated to another node, but that will be something that will happen, is we'll have the ability to have replicas take over if one of the nodes went down. But right now, like if one node goes down, that is down until you bring that up. There are some things though that you can do, like in terms of high availability, where you could have like active passive clusters, and a lot of it really depends on like where the data is coming from, right, and like how it's getting to NiFi. So you could have, if you're worried about running this in like a cloud scenario where you have like different zones and you're worried about, I don't want this whole zone to have a problem. There's a really long article that one of my coworkers wrote about all these different ways of architecting across zones. I think one of them was to actually split the cluster across zones. Another one is to have like an active passive cluster. So there are some things you can do today to sort of isolate, like narrow down what could really go wrong. But we do acknowledge that that idea of replication needs to happen. Okay, so site to site, we call this like direct communication between two NiFi instances. So a common scenario is that you have this like tiered collection of NiFi instances spread out all over the place, trying to bring data back to a central place. And you might funnel that through a couple of layers of instances, right? And so the way this works is there's two components that you can put onto the graph. There's input ports and output ports. And you can build a push model or a pull model directly between two NiFis. And this can work between two standalone instances, two clusters, standalone to cluster, like any combination, right? It doesn't matter. NiFi handles all that for you. So that's one of the really nice things. And if you are going from like a smaller standalone into a cluster, it handles the distribution for you. So it'll round robin the data between all the nodes. So you kind of get like that even distribution just by using this mechanism. So just kind of looking at how this works. And again, this doesn't have to be standalone to cluster. It's just easier to make the diagrams like that. So this is showing a push model. So in the first NiFi on the left, you'd bring all your data to RPG, it stands for Remote Process Group. That looks like a processor on the graph, but it actually represents a connection to the other NiFi instance. So you tell it the URL of the cluster manager or of the single instance, and then it communicates with it and learns about the cluster. So, pushing model, you have the other NiFi, has these input ports waiting to receive data, and it's distributing the data across them. In the pull model, it's sort of the reverse, right? The first NiFi brings data to this output port, and the data is sort of waiting there for something to pull it. And the second NiFi, if it's a cluster, it has each node pulling the data back, right? So typically, I think, I've seen more of a push model just because it lets the the first NiFi make the decision about like where to push it, but really doesn't matter. And the reason why I'm bringing this up is because this is a cornerstone of the integration between NiFi and Apex. And so the site-to-site code that does that between two NiFis, it's in its own module that we call the site-to-site client. And you can use it from any Java program. So if you just wanted to write like a quick, simple Java main program, you could use it to either pull data or send data to NiFi. And it makes it really nice to integrate with something like Apex, where it wants to have an input operator that pulls the data in, right? So that's going to kind of be the foundation of the integration there. Okay, so jumping into the operators or how this integration works. So like we said, we'll use the site-to-site client in the operators. We'll have input operators that can pull the data from NiFi into Apex, and then output operators if we want to send data back. And we kind of have this abstraction that you can pass around. You don't necessarily have to pass this around as a tuple, but one option is this NiFi data packet, which that's kind of like your flow file, right? So you're getting from NiFi the attributes and the content. And I think the nice thing about this is you can use NiFi to do a lot of the things that it makes easy, just like extracting values from text or doing some parsing and preparing data in those attributes without writing any code. And then by the time it gets to Apex, everything's set up, and then you can focus on more like the analytic part that you want to do, right? So you don't have to write as much maybe parsing code, things like that. So looking at the input operator.
Is that kind of similar to connecting by Kafka to Apex? Or?
It's similar concept to Kafka, right? So the question was, is pulling from NiFi into Apex similar to pulling from Kafka? Yeah, yeah, I think the overall concept is similar. Some of the differences are Kafka's not doing as much manipulation of the data, right? They're kind of like something delivers it to the topic and then it's available there to pull, but in the middle there, that's nothing's really happening there. So I think NiFi gives you that possibility to do things there. On the flip side, one of Kafka's advantages is it has the offsets, so the data is still available there and can, retry by resetting the offset. In the NiFi case, the site-to-site client does have a transaction mechanism, so it attempts to pull that data from the output port, and it then, once it thinks it's pulled all the data, it performs a checksum to verify it has it, and then confirms the transaction. So the data is not actually removed from that queue on the NiFi side until the side over here has confirmed that it has all the data and completed. So there is a mechanism there to handle that. So on the input operator side, sort of have like 3 levels here. The base class is this abstract NiFi input operator that provides the main interaction with like the site-to-site code, and then it delegates to like an abstract method to say how to actually create the tuples from what it's pulling in NiFi. And then we have the single abstract NiFi single port input operator, which adds the one output port. And then it's still waiting for another class to provide the implementation, which is the NiFi single port input operator. So that's like probably the most likely thing you would use is that last one there. And what that's doing is it has a single output port, and it's producing these NiFi data packets that you can then use. But these different levels kind of give you the flexibility where if you didn't want to produce NiFi data packets as your tuple, then extend one of the other ones and do something different, right? I know everybody, maybe not Java developers, I know it's hard looking at the code, but just like an example of how you'd use this operator, the main thing I wanted to point out was how you create this site-to-site client. So we have this builder where you specify the URL and the port name in NiFi that you want to pull from. So that URL is either the URL of a single instance or it's the URL of the cluster manager. And then, just for this example, I have the no-op data manager, window data manager, and then pass those in to create the operator. Here it's just hooking up to a console operator and then connecting them up. So it's just like writing out to the console each NiFi data packet. On the output side, similar, there's 2 output operators. Very similar. There's this concept of the data packet builder, which is sort of like the pluggable way of converting the tuples back to what you need to send back to NiFi, right? So it's like maybe I have strings coming into my operator, and I need to somehow turn that into the NiFi data packet that that sends back to NiFi. And looking at this example, very similar, how you'd set it up. Here, this port here would be an input port on NiFi because you're sending data back, whereas the other one was the output port pulling it. So I think that's kind of the overview on the operators. What I wanted to jump into was kind of an example of how to, maybe integrate these technologies. And I think when most people think about how to use NiFi, it's usually about moving data from like sources that are increasingly getting smaller and smaller, driving it all the way back to a central data center, and then an analytic platform like Apex, right? So you kind of always think of this, like, or at least I always think of this left to right data flow, right? And increasingly, as you move out to the edge, getting smaller and smaller. And I think where it gets interesting is kind of thinking about this like back and forth flow, right? Like prior, it's always kind of been, well, once you get it to the data center, you do some analytics, and that's sort of the end. But you can really do some pretty cool things if you take those results and push it all the way back, right? So you can do some like dynamically adjusting data flows where you're using those analytic results to change what you're collecting, or change something in your data flow like all the way out at the edge. So I tried to come up with an example that, it's admittedly not really using the power of Apex probably, but it is a working example between the two technologies and just kind of shows how this could work. So I came up with this like log collection scenario. I know it's a bit to look at here, but I'll try to walk through it. So I guess the idea is you have these edge instances collecting logs, trying to bring them back to the central data center. And initially we're saying that we only want to collect like error messages and warning messages because we don't really have the bandwidth or the power to bring back like every log message, right? It'd just be too much. So going across the top, we're bringing back logs from an edge NiFi to the core. And you would imagine there's a whole bunch of these edge NiFis. We deliver those logs to Apex. We can then do like a window calculation to determine a rate of how many of those error and warning messages we're getting. And we'd have like some kind of user provided threshold that said, I'm just making this up. If I get more than 100 of those a second, then I want to stay at the same level because that's like my max I could accept. But if it drops way below that level, then, well, okay, we're not receiving as many as we thought, so why don't we start collecting more? And we can tell the edge to adjust itself and start bringing back more. So the way we do that was, we'd use both sides of those operators in Apex to receive the logs, pull them in, do some calculation, and then write the results back to NiFi. And then NiFi would provide those results all the way back out to the edge. And I'll show what this looks like, exactly in NiFi and Apex. But so going across the top is kind of the bring the logs to the central location, then Apex sending back, storing the results, and then the edge instances will pull the central NiFi to say, like, give me your latest results, like, what should I be doing, right? So kind of look at how this could look in NiFi. So this was an example flow from one of the edge instances. So going across the top, tail file processor, watching a log file, right? And I'm sort of assuming for this example, it's just like your simple Java logging with like log4j, logback, where you have info, error, warn, those types of things. Split lines, basically, if it grabs a file with a bunch of log lines in it, it splits them into one line per flow file, so now I have like one log message. Extract text applies a regular expression to each one of them and can pull out what is the level. So I basically want to identify the info, error, or warn, and pull that from the text up into an attribute so that it's available there. And then the filter log level is where we're going to be filtering initially based on this input of filters that's in a file that tells it, like, only let things pass through this that match the filters I'm interested in. And then that box on the right there, that's the remote process group that's delivering back to the central NiFi. And along the bottom here, completely kind of disconnected from this, is this two processors that are actually polling the central NiFi and saying, like, what's your latest set of filters that I should be using to filter things? So they get HTTP processor, you provided a URL, and you can set it on a timer, so like every 30 seconds, make a request. And it's actually calling to a service embedded in the other NiFi, and when it gets the results, writing it to a file. Those results are the same filters that scan attribute is using up there. So that's how it's kind of tied together. And then looking at the central NiFi, Going across the top, it's just a pass-through, all the logs coming in, and that top output port there is where Apex would be pulling off that, right? And then when it's done and it writes something back, it would send it in here. Dictionary is just a term for the list of filters. Just, don't think too hard about that. And then it comes in there and it writes it to a file on disk so that it has it stored. And down here, basically building, this is one of the really cool things in NiFi. You could basically build a web service by just connecting these processors up. So this handle, HTTP request, is providing a web service at this port / dictionary. That path. And it's listening on a port that you can see in the processor. So that's how that other processor is calling over here and saying, like, let me retrieve your current set of filters. And it just goes and retrieves that same file that was stored and sends that back as the response. And then looking at this, kind of like the Apex application, again, it's not doing anything very complicated here, admittedly very simple, but just wiring up the input operator to pull in the data. There's this one log level window count operator that's producing, like, for this window, what are your counts of each level, and then the builder is actually determining the output of that builder. So if you look at this builder, the input is this log levels object, which is your map of levels. And then the output it's going to produce to send back is like this new set of filters. So it's either going to send back content of just error and warn, or it's going to send back error, warn, info, debug, and all the other levels, right? And then that'll go back to this output operator, and then write that back to NiFi. So that's kind of how you create, like, that full loop there. And just to kind of summarize, right? So you're sort of creating this full loop and adjusting, what's happening on the edge, right? And that's pretty much all I had. I think that's kind of the really interesting cases when you start doing something with those results. I put together that whole example there. I have that actual implementation with those templates for NiFi and everything, and some instructions that probably need to be made better. But you could theoretically try to get that running from that GitHub repository there. I'm trying to build out the same example with some different frameworks. So right now there's Apex and Flink. Maybe if somebody knows one of the other frameworks better and they want to contribute, that would be pretty cool. I'll take any questions anybody has.
Question online. Any questions on the webcast? Any questions on webcast, guys? Okay, cool. So thanks a lot, Brian, and Ilya, thanks a lot. So this was our first meetup in this office. Hope to see you guys soon. We're gonna have a lot more meetups coming up. And meanwhile, make sure you get your t-shirts. There's still pizza out there. Yeah.